Alright everybody, this video is about the first topic of chapter 5, covalent bonds. We all know what covalent bonds are, okay? Well, they usually form between non-metal elements, but here in this topic, we're going to discuss more properties of covalent bonds. Okay, we will introduce a very important concept, electronegativity, and we will learn how we use electronegativity to decide or identify the bond polarity, okay, or compare which covalent bond is more polar. Well, I hope this slide looks familiar to you. Okay, essentially this slide shows us the noble gas core electronic configurations of the first 20 elements, and also the Lewis dot valence electronic configuration of those elements. Okay, so for instance, carbon, 4 dots represent the 4 valence electrons on the 2s, 2p orbitals. Phosphorus, 5 dots, okay, 1 pair and 3 unpaired electrons represent 5 valence electrons on the 3s and 3p orbitals. Okay, and we've already discussed the Duet rule and the Octet rule, and we said that some of the elements they prefer 2 electrons in the outermost electronic shell. Some of the elements, okay, prefer 8 electrons in the outermost electronic shell. And we used these two rules help us identify understand the electron transferring process of ionic compound, for instance, lithium and fluoride. Okay, let's just use these two elements. We know that lithium has 1 electron, 1 valence electron on the 2s orbital. Fluorine has 7 valence electrons on the 2s and 2p orbital. Okay, and when we have those two atoms interacting with each other, lithium will transfer this electron to fluorine, because lithium, after it loses this electron, okay, it will have helium or 1s2 as the electronic configuration for lithium plus. Okay, so it's going to be stable. Okay, and for fluoride, since it has 7 valence electrons, it has a tendency to accept 1 more electron. Okay, to satisfy the octet rule, which means 8 electrons in the outermost electronic shell for fluorine. Okay, so after the electron transfer process, lithium becomes lithium plus, fluorine becomes fluoride, and so the cation and anion will bind to each other to form lithium fluoride. Okay, so this is an ionic compound. How about covalent compound? How does Duet rule and Octet rule help us understand the electron sharing nature of covalent bond? Let's use water as an example. We saw the Lewis structure of the water molecules before, but let's take a closer look and let's revisit. Okay, essentially, well, we know water has 1 oxygen and 2 hydrogens. Okay, oxygen 6 valence electrons and hydrogen 1 valence electrons. Okay, I'm going to use black color. How about green? Okay, so hydrogen and hydrogen. Okay, so how do we understand the Octet rule and Duet rule for those elements when they form covalent compound, water? Okay, remember hydrogen, according to Duet rule, it wants to get 1 more electron to have 2 electrons in the outermost electron share, which is 1s for hydrogen. Okay, for oxygen, 6 valence electrons, so it has a tendency to obtain 2 more electrons to satisfy the Octet rule. Okay, so when the 2 hydrogens and 1 oxygen interacting with each other, what will happen is, okay, it will form water molecule, And in this water molecule, oxygen will share one electron with one hydrogen, okay? So as you notice that now you have two electrons shared by one oxygen-hydrogen pair. And for this hydrogen, it has two electrons now. For this hydrogen, it has two electrons now because these two electrons will move around both hydrogen and oxygen, okay? Electron sharing, remember? So both hydrogens are happy. How about oxygen? Well, for oxygen, if you count the number of electrons, one pair, two pairs, three pairs, and four pairs. So for oxygen, now it has 8 electrons. Okay, so it looks like by sharing the electrons, all three members are happy in this molecule. Okay, so this is how we use octets and duet rules for us to understand or how we come up with the Lewis structure of covalent compounds. We'll have more practice later on in this chapter, but here the take-home message is duet rule and octet rule can help us understand how those non-metal elements, okay, receive or donate or lose electrons to satisfy to share electrons to form covalent bonds. All right. And further study of covalent bonds shows a very important property of covalent bond, and that is the polarity. What does that mean? Well, here this molecule is hydrogen fluoride, okay? And hydrogen fluoride is between hydrogen and fluoride, between these two atoms, okay? They will share one pair, okay? Now, if you take a look at the again, let's just count the electrons. Hydrogen now has 2 electrons, duet rule. Fluorine now has 8 electrons, octet rule. So both members are happy. So this is the a stable covalent compound, okay, with one covalent bond. Now, if you put those HF molecules between two metal plates, okay, right here, well, you will notice that those hydrogen fluoride molecules just move around randomly without any particular directions. But once you put the charge on the two plates, one is negative, the other one is positive, and you will see that those hydrogen fluoride molecules line up. Okay, one side of the hydrogen fluoride molecule pointing to the positive metal plate, and the other side of the hydrogen fluoride molecule pointing to the negative the metal plate with negative charge. Okay, so it looks like once you have those positive charge and negative charge metal plates on the two sides, then those molecules, okay, the two sides of the molecules can be attracted by the two different plates. So that's why all of them get lined up. Okay, so what does that tell us? Well, it tells us for this hydrogen fluoride molecule, one side is negative charged and the other side is positive charged. And because of this, this negative charged side is attracted by the positive metal plate. Positive side of the molecule get attracted by the negative metal plate. That's why all of the molecules line up. Then particularly which side of the HF molecule is negative, which side is positive? Well, if you remember the octet rule and duet rule, okay, fluoride likes electrons because it wants to get electrons to satisfy octet rule. And hydrogen, it wants to get electrons to satisfy duet rule. Unfortunately, fluoride has a better attractive force towards the electrons. Therefore, even if you have HF, this two atoms sharing 2 electrons, they share these two electrons unevenly. In other words, fluoride will attract these two electrons better. Okay, those two electrons are going to move around fluoride most of the time. Sometimes they can move to the hydrogen side, but most of the time they're going to be on the fluoride side. Now, when you have electrons move around fluoride side most of the time, that means that fluoride side would be negatively charged. And because hydrogen, when you compare that with fluoride, it lacks of the electrons, right? So this side would be positively charged. Okay, so that's the reason why the HF molecule has a negative side and positive side. Okay, and the further study noticed that the different covalent bonds will have different polarity. For instance, if you compare HCl, and again, according to what we discussed, chlorine will have a better attractive force towards the two electrons shared by hydrogen and chlorine. Therefore, this side would be negatively charged and hydrogen side would be positively charged. So this is also polar. Well, we know that this is polar, but study found that this side is, or this HF molecule is more polar than HCl molecule. So the question is, how do we identify, how do we determine which bond is more polar, which bond is less polar? Do we have a standard? Well, let's introduce the electronegativity. Electronegativity is closely related to the bond polarity. How do we define it? Electronegativity, we use cap En to represent electronegativity, okay, sometimes. Is the ability of an atom to attract electrons to itself in a chemical bond. And here, it can work on both ionic bond and the covalent bond, okay? This picture shows you the trends of electronegativity across periodic table. Two trends. When you move from top to bottom in the same group, electronegativity decreases. Okay. When you move from your left to right across the same period, electronegativity increases. I need you to understand and remember those two trends. Okay. Well, let's talk about each group. Let's take a look at the group 17 from fluorine to the element At. Well, if you take a look at those numbers, fluorine has an electronegativity of 4.0, the highest in the periodic table. But At here has only an electronegativity of 2.2. Okay, so from top to bottom, electronegativity decreases. In other words, fluorine has higher attractive or stronger attractive forces towards electrons compared to the other elements in group 17. Similar trends can also be observed in group 1, from hydrogen to francium. As you can see, the number decrease when you go from top to bottom. So that means hydrogen has a stronger attractive force towards the electron than the other elements in group 1. Okay. How about each period? Well, let's just use the third period from sodium to chlorine. When you move from sodium to magnesium, aluminum until you reach chlorine, as you notice, the number increase, electronegativity increase. That means the chlorine has much higher attractive force towards the electron than the other elements in the third period. Okay, so these are the trends of electronegativity across the periodic table. With this information, let's take a look at electronegativity differences. How we use electronegativity difference, delta En. Delta means most of the time means difference. Okay. How do we use delta En to determine the bond type and the polarity of covalent bonds. Okay. Well, here this table from your textbook shows you that the delta En, if the delta En is between 0 and 0.4, then because the electron negativity difference is so small, basically the two atoms will share the electrons evenly. So this bond is nonpolar covalent bond, like chlorine. Okay, chlorine right here, because these two chlorine atoms will share the electrons equally. So for this chlorine molecule, there is no negative side or positive side. Therefore, this is a nonpolar covalent bond. Okay. If the delta En is between 0.4 and 20, then we said that this bond is going to be polar. And if this bond is covalent bond, of course, we're going to call it polar covalent bond, like HCl. Okay. For HCl, you can see that as one of the examples we talked about a moment ago, because chlorine has a higher electron negativity than hydrogen. In other words, chlorine will attract the shared electrons better. So most of the time, electrons will move around chlorine. Occasionally, electrons will move to the hydrogen side, but not very much. Okay, so since chlorine attracts most of the electrons, so chlorine side would be negatively charged, hydrogen side would be positively charged. That generates the polarity in this case. Okay, if the electron negativity difference is above 2.0, then that means the electrons will be transferred from one element or one atom to another atom completely. Okay, so they are not going to share electrons anymore, because the element with higher electron negativity will just grab the electron from the atom with less electron negativity completely. Therefore, you generate cations and anions. You form ionic bond, like a sodium chloride. Okay, so they are not sharing electrons, and instead cations and anions. Okay, of course, ionic bond is going to be polar, no doubt about that. Okay. All right. Before we talk about how we identify the polarity of covalent bond, how we identify which covalent bond is more polar, let's introduce dipole moments. Okay. Dipole moment, we use mu to represent dipole moment. Here, this is the calculation equation for dipole moment. Q, magnitude of charge. R is the distance. This equation is not required in this class. We just need to use the dipole moment to tell us how polar a bond is. Okay, so let's take a look at this table. This table shows you the delta En of four compounds, okay, and also the corresponding dipole moment of them. Okay, well, as you notice, the chlorine, the delta En is 0, so for the chlorine-chlorine bond, it's nonpolar, so dipole moment is 0. For ClF, delta En is 1.0, okay, and dipole moment is 0.88. It looks like because of the electron negativity difference is 1, okay, in this intermediate window, the ClF bond is going to be polar, so the dipole moment is higher than 0. Okay. Now, if you take a look at the HF, delta En is 1.9, which is quite high in this window, very close to 2.0. So again, HF is going to be a polar bond, and you can see dipole moment of HF bond is 1.82. It's much higher than the other two, right? So very polar. For lithium fluoride ionic compound, you can delta En is 3.0, larger than 2.0. So dipole moment is extremely high. Okay, so it looks like the larger the delta En, the greater the dipole moment is. Okay, so there is a trend. Let me write the general trends, okay, between the delta En dipole moment and the polarity. Okay, so the bond polarity, so you can better understand the whole relationship. When you have larger delta En increase, dipole moments will also increase. Moments will also increase, and that means bond polarity will increase. On the other hand, if you have lower delta En or smaller delta En, then the dipole moment will also be smaller. That means the bond polarity will be lower. Okay, I want you to be very clear about those two trends. Okay, because it will help us identify which bond is more polar, which bond is less polar. What do I mean? Let's take a look at this example. Okay, well, this question asks you to arrange the following covalent bonds in an order of increasing bond polarity. Well, if you can identify the delta En trends of those bonds, then you should be able to, identify the trends of the bond polarity, right? So how do we identify the delta En trends? Well, before you do that, you have to identify the trends of electron negativity of those elements first. Okay, let's take a look at the example A. You have a fluorine, sulfur, oxygen, and selenium. Okay, if you take a look at this periodic table, fluorine is high above here, right? Sulfur, selenium, and oxygen here. Oxygen, fluorine, they are in the same period. So according to the electron negativity trend of in the same period, fluorine will have higher electron negativity than oxygen. Remember, across each period from left to right, electron negativity increase. Okay, so fluorine has a higher electron negativity than oxygen. And oxygen, sulfur, selenium, they are in the same group. And when you go from top to bottom, in the same group, electron negativity decrease. Okay, so that means for those four elements, electron negativity of those four elements in increasing order would be selenium, less than sulfur, less than oxygen, less than fluorine. Okay. Well, now, based on this information, we should be able to identify the trends of electron negativity difference. Well, when you look at this, oxygen, fluorine, oxygen has lower electron negativity than fluorine, okay? But the difference between the two certainly is less than the difference between sulfur and fluoride, because sulfur and fluoride, they are further away from each other across the periodic table, okay? Or in this sequence. Therefore, delta En for sulfur, fluorine, apparently is going to be larger than the delta En of oxygen and fluoride. Okay, same idea for selenium, fluoride, because they are on the two sides of this sequence of this order. The difference, electron negativity difference between the selenium and the fluoride would be quite high, okay, higher than the other two pairs. Okay, what do I mean? So let's just go ahead and write the electron negativity difference trend. Delta En for FO bond is less than delta En of S bond is less than delta En of F Se bond. Okay, so essentially you can see that the electronegativity difference trend can be determined based on the relative positions of those elements on this sequence here. Okay. Now, based on what we just discussed on the last slide, the electronegativity difference can tell us the bond polarity. Higher electronegativity difference will give greater bond polarity. Therefore, the bond polarity in the increasing order would be fluorine-oxygen bond is less polar than fluorine-sulfur bond, less than fluorine-selenium bond. Okay, so example B. Okay, you have chlorine elements, phosphorus, silicon, and sulfur. Okay, now if you can take a look at the positions of those elements, chlorine, sulfur, phosphorus, and silicon, remember across the period, each period from left to right, electronegativity increase. Okay, therefore, for these 4 elements, the increasing order of electronegativity would be silicon, less than phosphorus, less than sulfur, less than chloride. Okay, and again, based on the relative positions of those 4 elements in this sequence, the delta En chlorine would be less than delta En of chlorine sulfur, less than delta En of chlorine phosphorus, and then less than delta En of chlorine silicon bond. Okay, and then based on the delta En order, we can decide the bond polarity. Chlorine-chlorine bond, essentially it's nonpolar, right? So it's less polar than chlorine-sulfur bond, less polar than chlorine-phosphorus bond, less than chlorine-silicon bond. Okay, so this is how we determine which bond is more polar, which bond is less polar. It's based on the electronegativity difference, and the electronegativity difference is based on the trends of electronegativity across the periodic table. All right, we'll do more practice in our lecture, and we'll see more examples.